Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In this video, we're going to dive deeper into the log level model, the mathematical derivation, so from logs to exact percentage change effects. It is very likely that depending on the book that you're using and also the convention that your professor or lecturer has decided for the course you're taking, most of the times you are going to use for the log level model an approximation where you simply multiply your beta 1 hat by 100. However, there is a more exact formula, which is what we're going to see in this video. So let's start by the model, which is ln y equals to beta 0 plus beta 1x plus some error term. Now, what we're going to assume in here is that the conditional expectation of the error term on x is equal to 0. And that means that if we take the expectation, the conditional expectation of the ln y on x, that should give us simply beta 0 plus beta 1x, because the expectation of the epsilon term on x should be 0, and that should disappear from that expression. So this is the population regression function. Now, let's take the derivative from this expression. So we're going to have the derivative expectation of ln y conditional on x with respect to x being equal to simply beta 1, because the beta 0 here does not have an x attached to it, so it's a constant. Derivative is going to be 0. Now, what you should know in general, and if you don't know, that's completely fine, because we're going to have a separate video showing you step by step this property. So this is what you should be knowing, basically. The derivative, so when we have ln of y with respect to x, this is going to be equal to 1 over y dy over dx. Okay, so if you don't know where this formula is coming from, don't worry, because the next video is going to show you a very short video exactly where that is coming from. So from here, we can actually write that 1 over y dy over dx, because this is what we have. We already know this expression because we just got here the beta 1, so that should be equal to beta 1. And if we send now this y on the other side, or multiply both sides by y, however you want to do it, then we're going to get dy over dx equals to b1 times y. Now, let's divide, let's look into what exactly each of these sides is telling you. The left-hand side, especially if we look at this first part that we have in here, this left-hand side in here, that is exactly the percentage change in y. Percentage change in y, okay? So overall, what we're saying is that a 1 unit increase in x changes y by approximately this beta 1 in here, which normally we'd have to multiply with 100 to turn into a percentage. So 100 beta 1%. That's the approximation. Now, let's show it a little bit more clearly with the most specific formula. If we take ln of y1 equal to beta 0 plus beta 1x, then we take ln of y2, which is by increasing our x simply by 1, so beta 0 plus beta 1x plus 1. So this is going to follow a little bit the convention, or what we saw in the previous video on what the ln function does. So from here to here, x has increased by 1 unit. So let's see what happens to the ln. If we subtract both, we're going to get ln y2 minus ln y1 equals to simply beta 1. Because normally in here you would have had x plus 1 minus x, and x would cancel out, so it would just remain as a beta 1. Using log properties, then we are going to see simply that ln of y2 divided by y1 is equal to beta 1, which means that y2 divided by y1, it's e to the power beta 1. From here, y2 by itself is simply y1 times e to the power beta 1. Okay, now if we wanted to compute the exact percentage change, we would normally have y2 minus y1 divided by y1, not just y2 over y1. But now we know what y2 is because we just found a relationship between that and y1. So we can write these as y1 times e to the power beta 1 minus y1 divided by y1. And if you factorize the y1, you're going to be left with e to the power beta 1 minus 1 divided by y1, where y1 cancels out, which means that you'll be left with simply e to the power beta 1 minus 1. Now, if this is just the change, so obviously if you wanted percentage change, you'd have to multiply this by 100%, which means in here also by 100%. Okay? And this is that exact percentage change in y when x increases by 1 unit. Books most of the time introduce this formula first and then just mention in a one-liner, well, you can just use the approximation multiplication by 100. But otherwise, this is the exact formula. And when beta 1, so let's see the relation between the two. The idea is that when beta 1, and let's put the hat here, is small, then the expectation of beta 1 hat minus 1 is going to be approximately exactly beta 1. Okay? And that's why we do that approximation here by saying, well, let's just multiply the beta 1 by 100. So that's a very good estimation. Now, for larger coefficients, so when the beta 1 is large, it's usually better to use this formula. But most of the times, whether it's a big or a large one, your lecturers might also, for ease of computations, especially if it's an exam where calculators are not allowed, would allow you to just do the approximation with the 100. I hope this was helpful, and I'll see you in the next video.